Tonight, in the stillness between breaths, your body whispers a secret older than mountains, deeper than oceans, stranger than any story ever told. Right now, as you settle into this moment, you are carrying passengers. Trillions of them. Atoms that have journeyed across unimaginable distances and incomprehensible spans of time just to arrive here, tonight, arranged in the temporary pattern that calls itself you. Close your eyes and feel the weight of your hand. That weight, that solid presence is an illusion of stability, because every single atom in that hand, the calcium in your bones, the iron in your blood, the oxygen in your lungs, is a time traveler. Not metaphorically, not poetically, literally. Before we begin this journey through your own ancient architecture, if you find something interesting here tonight, a gentle like or subscribe to Space Doze would mean everything. It's a small gesture, but it tells me you're out there breathing with the cosmos, ready to drift through these mysteries alongside me. Now, settle deeper into the stillness, because these atoms have witnessed the birth of galaxies. They've drifted through clouds of gas larger than solar systems. They've been crushed in the hearts of dying stars, scattered by explosions that briefly outshone entire galaxies and swept across light years of empty space in cosmic currents that flow like rivers through the dark. Some of the hydrogen in your body has been cycling through the universe for 13.8 billion years. The carbon that forms the backbone of every protein, every strand of DNA, every thought you've ever had, it was forged in stellar furnaces that burned and died before our sun even existed. You are not separate from the cosmos. You are not a visitor here, an accidental arrangement of matter in an indifferent void. You are the cosmos itself, temporarily gathered into a form capable of looking back at its own vastness and asking, where did I come from? Tonight, we're going to answer that question. Not with abstractions or distant philosophical musings, but by tracing the actual physical journey of the atoms inside you. We'll follow them from the first explosive seconds of creation through the blazing hearts of ancient stars, across the spiral arms of galaxies, through clouds of cosmic dust, into the formation of our solar system, and finally, after billions of years of wandering, into you. This isn't a story about space out there. This is a story about the space inside you. The universe didn't just create you, it became you. Every atom carries a history written in nuclear fire and gravitational dance. And tonight, in the quiet dark, we're going to read that history together. What we're about to explore will change how you feel sunlight on your skin, how you see the night sky, how you understand the very sensation of being alive. You are about to remember that you are not in the universe. You are the universe, briefly awakened to itself. Let's begin where everything began. Not with your birth, not with Earth's formation, but with the first breath of creation itself. There's a peculiar loneliness that comes with being human. We stand beneath the night sky and it feels distant, unreachable, other. We see those points of light scattered across the darkness, and something in us whispers that we are separate, that we are small, temporary things watching vast, eternal forces from the outside. This feeling of separation runs deep in human consciousness. We build walls between categories, living and non-living, organic and inorganic, earthly and celestial. We speak of going into space as if space was somewhere else, somewhere we don't already inhabit. We look at stars and see them as distant objects, beautiful perhaps, but fundamentally alien to our experience. The ancient Greeks divided the cosmos into two realms: the earthly sphere, messy, changeable, mortal, and the celestial sphere, perfect, eternal, unchanging. Even after Galileo, shattered that division by pointing his telescope at the imperfect, crater-marked moon. Something of that separation lingered in human thought. We are here. The universe is out there. But this separation is an illusion, not a comforting philosophical statement. An actual, demonstrable falsehood revealed by physics and chemistry, and the patient work of astronomers who spent decades measuring the light from distant stars. You are not watching the universe from some separate vantage point. You are not an alien intruder in an indifferent cosmos, a biological accident clinging to a rock, separate from the grand mechanisms of creation and destruction playing out in the depths of space. That narrative, however poetic it might seem, is wrong. You are a conscious expression of cosmic processes that have been operating for nearly 14 billion years. The same forces that ignite stars and forge galaxies are operating right now in your cells. The nuclear reactions that power the sun are the ultimate source of energy for every thought you think, every breath you take. The gravitational collapse that creates stellar cores also created the planet beneath you. The quantum mechanics that governs particle behavior in distant nebulae also governs the chemical bonds holding your body together. There is no line where you ends and the universe begins. That boundary we draw, that feeling of being a separate self contained in skin, it's a useful fiction, a necessary illusion for navigating daily life. But it's not true. Not at the deepest level. When astronomers look through telescopes at the death of a star 50 million light-years away, they're not looking at something foreign. They're looking at the same process that created the atoms in their eyes, in the telescope, in the planet beneath their feet. When they analyze the spectrum of light from a distant galaxy, measuring the ratios of elements in that ancient starlight, they're reading their own family history. You are not separate. You have never been separate. The story of the universe is not something that happened to someone else, somewhere else, somewhen else. It is your story. The atoms in your body are not visitors from space. They are space temporarily organized into a pattern complex enough to wonder about its origins. And that pattern, that temporary arrangement you call yourself, carries a history so vast and violent and beautiful that it defies imagination. A history we're about to trace, atom by atom, from the beginning of time to this present moment. In 1980, Carl Sagan stood before a television camera and spoke a sentence that would echo through generations. "We are made of star stuff." It became one of the most quoted phrases in popular science. Beautiful, poetic, inspiring, and completely, literally, factually true. Not a metaphor, not an approximation, not a romantic notion meant to make us feel connected to something larger. When Sagan said we are made of star stuff, he was stating a precise scientific fact about the origin of the atoms in your body. Every element heavier than hydrogen, every carbon atom, oxygen atom, nitrogen atom, calcium atom, iron atom in your body was created inside a star. Not near a star, not influenced by a star. Inside. In the nuclear furnace of a stellar core, where temperatures reach tens of millions of degrees, and pressures crush matter into states that don't exist anywhere else in the universe. Hydrogen, the simplest element, was born in the first minutes after the Big Bang. But hydrogen alone can't build a brain, can't form a bone, can't carry oxygen through blood. For that, you need complexity. You need carbon to form the backbone of organic molecules, oxygen to burn fuel and release energy, nitrogen to build proteins, phosphorus to store genetic information, iron to transport oxygen, calcium to provide structure. None of these elements existed in the early universe. The cosmos that emerged from the Big Bang was simple, just hydrogen and helium, the two lightest elements, with a trace of lithium. That's it. No carbon, no oxygen, no possibility of chemistry complex enough to support life. For nearly 14 billion years, the universe has been running a slow alchemy, transforming simple matter into complex matter through processes so violent they can only occur in stellar cores and supernova explosions. Stars are not just lights in the sky. They are factories, forges, crucibles where the raw material of existence is transformed into the building blocks of planets and oceans and living things. Your body contains approximately 7 octillion atoms. That's 7 followed by 27 zeros. 7,000 atoms. Each one has a biography, a journey, a history of transformation. Tonight, we're going to trace that journey. We're going to follow a single atom, let's call it a carbon atom in your left index finger, backward through time. We'll watch it cycle through your body, absorbed from food, which absorbed it from plants or animals, which absorbed it from air or water or soil. We'll trace it back through Earth's geological history, back to the formation of the solar system 4.6 billion years ago, back through the collapse of a giant molecular cloud, back to the death of an earlier star that scattered it into space, back to the nuclear reactions in that star's core that created it, back through previous stellar generations, back to the first stars that lit the universe. We'll travel 13.8 billion years across light years of space, through temperatures of millions of degrees and densities beyond comprehension. And at the end of this journey, you'll understand something profound. You are not just in the universe. You are not just of the universe. You are the universe, briefly awake and aware, asking questions about itself. The journey begins. Take a breath. That oxygen you just inhaled? Let me tell you where it came from. In the beginning, there was no space to drift through, no time to measure, no atoms to tell stories. There was only an infinitesimal point of infinite density and temperature, a singularity that defies our everyday understanding of physics. And then, 13.8 billion years ago, that singularity began to expand. Not an explosion into space. Space itself was expanding, carrying energy outward, cooling as it stretched. In the first trillionth of a second, the universe inflated faster than light, doubling in size over and over in an instant so brief it has no meaningful human comparison. This was inflation, a cosmic exhale that set everything in motion. But the atoms in your body? They didn't exist yet. The universe was far too hot. Matter as we know it couldn't survive. Instead, there was only a seething ocean of energy so intense that particles and antiparticles flickered in and out of existence, annihilating each other in bursts of pure radiation. Then, as the universe continued expanding and cooling, something remarkable happened. Around 1 second after the beginning, temperatures dropped to about 10 billion degrees Celsius, still unimaginably hot, hotter than any star's core, but cool enough for protons and neutrons to survive without immediately being torn apart. And in the next 14 minutes, the universe became a fusion reactor. This period, called Big Bang nucleosynthesis, was a brief window when the entire cosmos acted like the core of a star. Protons, simple hydrogen nuclei, collided and fused. Some became deuterium, heavy hydrogen with an extra neutron. Deuterium nuclei fused to form helium-3. Helium-3 fused to create helium-4, the stable helium that would become the second most abundant element in the universe. 15 minutes. That's all it took. The cosmic temperature dropped below 100 million degrees, and fusion stopped everywhere at once. The opportunity window slammed shut. By the time the universe was 20 minutes old, its primordial alchemy was complete. The result? A cosmos made of approximately 75% hydrogen and 25% helium by mass, with trace amounts of deuterium, helium-3, and lithium-7. Nothing heavier, no carbon, no oxygen, no iron. Just the simplest elements spread throughout an expanding fireball that would one day cool into the starry universe we inhabit. Every single hydrogen atom in your body, about 60% of your atoms by number, was created in that 15-minute window. The hydrogen in your water molecules, the hydrogen in your organic compounds, the hydrogen that will eventually carry away heat when you sweat. All of it, manufactured in the universe's first quarter hour. Think about that. The hydrogen atom in the water molecule you'll drink tomorrow morning is 13.8 billion years old. It has existed since the universe was minutes old. It has drifted through space for eons, been part of countless stars and nebulae and planets, cycled through oceans and clouds and living things, and finally arrived in you, still fundamentally unchanged since that ancient cosmic forge went cold. This hydrogen is the oldest matter in your body. It predates stars, it predates galaxies, it predates everything except the expansion of space-time itself. You are carrying pieces of the universe's childhood inside you, right now, incorporated into the very structure of your cells. But hydrogen alone couldn't make you. For that, the cosmos needed to build something more complex. And that would require a very different kind of furnace. There's something deeply unsettling about the hydrogen in your body. Not dangerous, comforting actually, once you sit with it long enough. But unsettling first. That hydrogen atom has been conscious of itself for only the tiniest fraction of its existence. For 13.8 billion years it drifted, unconscious, unthinking. Just a proton with its electron companion, obeying physical laws, moving through space, occasionally bonding with other atoms, separating, bonding again. It was part of the first generation of stars, those massive, short-lived giants that formed when the universe was only a few 100 million years old. It drifted in their atmospheres, perhaps, or orbited at a distance, watching as they lived fast and died violently. When those stars exploded, the hydrogen was pushed outward by the blast wave, swept into interstellar space at thousands of kilometers per second. It floated in molecular clouds, those vast cold regions where gas and dust gather in concentrations so low, they're better vacuums than anything we can create in laboratories. It might have been part of a comet in some long-dead solar system, frozen into ice for billions of years, occasionally heated when its orbit took it near an ancient sun. It was certainly part of the giant molecular cloud that collapsed to form our solar system 4.6 billion years ago. As that cloud contracted under its own gravity, spinning faster, heating up, the hydrogen found itself in the swirling disk of gas and dust around the newborn sun. Some hydrogen fell into the sun itself, destined to be fused into helium. Some escaped entirely, blown away by the solar wind. But some, a tiny fraction, ended up in the planets. Earth captured hydrogen in its water, locked it in minerals, held it in the atmosphere. For billions of years, that hydrogen cycled through geological processes. It was part of primordial oceans, evaporated into clouds, rained down on lifeless continents, dissolved minerals, flowed in rivers that carved canyons long before anything lived to see them. Then, roughly 3.8 billion years ago, something extraordinary happened. Some of Earth's hydrogen became part of the first self-replicating molecules. Life emerged, still debated exactly how, but it happened. And suddenly, hydrogen atoms found themselves incorporated into living structures. Bacteria, archaea, eventually complex cells, multicellular organisms, plants, animals, Your particular hydrogen atoms have been part of countless organisms. They've been in bacteria in deep ocean vents, in plankton drifting through ancient seas, in ferns growing in carboniferous forests 300 million years ago, in dinosaurs drinking from rivers, in early mammals scurrying through the undergrowth, in your ancestors perhaps, stretching back through the evolutionary tree. And now, tonight, some of those ancient hydrogen atoms are in you, temporarily. You'll exhale some as water vapor, excrete some as urine, shed some in skin cells. They'll return to the environment, be absorbed by other organisms, continue their journey through the biosphere and geosphere. You are not the owner of these atoms. You are their temporary caretaker, a brief pattern they pass through on a journey that began when the universe was 15 minutes old and will continue long after you've returned them to the world. The hydrogen remembers nothing, but it has witnessed everything. But here's the beautiful problem the universe faced. After those first 15 minutes, hydrogen and helium can't do much. They're too simple. Hydrogen has one proton. Helium has two. These atoms can form simple molecules, H2, molecular hydrogen, for instance. But they can't build complexity. They can't create the rich chemistry necessary for rocks, oceans, or living things. Imagine trying to write a novel using only 2 letters of the alphabet. You could make a few words, perhaps, simple patterns, but you couldn't express complex ideas, couldn't build elaborate structures of meaning. That's the universe after Big Bang nucleosynthesis. A cosmos with a vocabulary of just 2 letters, trying to write the story of existence. For rocky planets to form, you need silicon, magnesium, iron, nickel, elements that can bond together to create solid structures. For water, you need oxygen. For organic chemistry, you need carbon to form the backbone of complex molecules, nitrogen to build proteins, phosphorus to store genetic information. For breathable atmospheres, you need oxygen in molecular form. None of these elements existed after the Big Bang. The early universe was incapable of producing them. The temperature and pressure conditions that create heavier elements, what astronomers call metals, meaning anything heavier than helium, simply didn't exist throughout space anymore. The cosmic fusion window had closed. So for hundreds of millions of years, the universe remained simple. Just hydrogen and helium gas, cooling and spreading, growing more diffuse as space expanded. In the cosmic dark, with no stars yet born, there was nothing to see, nothing to illuminate the vast expanses. This was the cosmic dark age, a period when the universe contained matter but produced almost no light. The building blocks of complexity, the elements that would eventually make planets and people possible, didn't exist yet. They would have to be manufactured. But that manufacturing process would require conditions even more extreme than the Big Bang itself, conditions that could only exist in one place: the hearts of dying stars. To forge the carbon in your cells, the oxygen in your lungs, the calcium in your bones, the iron in your blood, the universe needed to create stellar furnaces. It needed gravity to pull hydrogen and helium together into massive clouds. It needed those clouds to collapse under their own weight, heating as they compressed, until nuclear fusion ignited at their cores. The universe needed to make stars, and then it needed those stars to die. This is where your story truly begins. Not in the first 15 minutes of creation, but in what came after, when the cosmos learned to transform simplicity into complexity, one stellar death at a time. For hundreds of millions of years, the universe drifted in darkness, a void of hydrogen and helium, cooling, expanding, waiting. No stars burned, no light pierced the cosmic night. If you could have existed then, floating in that ancient emptiness, you would have seen nothing. Felt nothing but the faint warmth of the cosmic microwave background radiation, the afterglow of creation itself, slowly fading as space stretched. But gravity never sleeps. Even in that darkness, invisible forces were at work. The universe wasn't perfectly uniform. Quantum fluctuations in the first instant of inflation had created tiny variations in density, regions where matter was ever so slightly more concentrated than elsewhere. And gravity amplifies inequality. Denser regions pulled more matter toward them, becoming denser still. Over millions of years, these subtle variations grew into real structures. Clouds of hydrogen and helium, hundreds of thousands of times more massive than our Sun, began to form in the void. And then, somewhere between 100 and 200 million years after the Big Bang, something miraculous happened. One of those massive clouds collapsed under its own gravity. As it contracted, it heated. The gas particles falling inward moved faster and faster, colliding with increasing violence. At the cloud's center, temperatures climbed, 1 million degrees, then 10 million, then 100 million. The pressure became immense, crushing hydrogen nuclei together despite their electromagnetic repulsion. And fusion ignited. The first star was born. We've never seen one of these primordial giants. They existed too long ago, their light stretched and redshifted by the expansion of space, now too faint and distant to detect even with our most powerful telescopes. But we can calculate what they must have been like, and the numbers are staggering. These population 3 stars, so named because they were discovered theoretically after population 1 and 2 stars were already classified, were monsters. Not the modest, long-lived stars like our Sun. These were titans, perhaps 100 to 300 times the Sun's mass, burning with ferocious intensity. Their cores reached temperatures exceeding 100 million degrees Celsius. They shone with the light of millions of suns, their surfaces blazing at temperatures of 100,000 degrees or more, radiating primarily in ultraviolet light that would sterilize any planet foolish enough to orbit nearby. But they lived fast and died young. A star like our Sun, modest and patient, will burn for about 10 billion years. These first giants? Maybe only 2 or 3 million years. Some of the most massive might have survived barely 1 million years before their cores, having fused hydrogen into helium with reckless abandon, began their inevitable collapse. These stars were the universe's first alchemists. In their cores, for the first time since the Big Bang, nuclear fusion was creating elements heavier than helium. Carbon formed through the triple alpha process. Oxygen emerged as helium nuclei fused with carbon. Neon, magnesium, silicon, step by step, the periodic table was being written in nuclear fire. And when these giants died, they didn't fade quietly into the night. They exploded. Picture a star 200 times more massive than our Sun, burning through its fuel in barely 1 million years. In its core, fusion has progressed through multiple stages. Hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, neon to oxygen and silicon. Each stage lasting shorter than the one before, like a countdown accelerating toward an inevitable conclusion. Finally, silicon fuses into iron. And there the alchemy stops. Iron is special. It's the most stable nucleus in the universe. Fusing iron requires energy rather than releasing it. So when the core becomes predominantly iron, fusion ceases. The furnace goes cold. And without the outward pressure of fusion to balance gravity's inward pull, the core has nothing left to resist with. What happens next occurs in less than a second. The iron core, roughly the mass of our Sun but compressed into a sphere the size of Earth, collapses. Not slowly, catastrophically. In a quarter of a second, it implodes from Earth-sized to city-sized. The density becomes so extreme that protons and electrons are crushed together, forming neutrons. The collapse rebounds, sending a shockwave of unimaginable violence racing outward through the star's outer layers. This is a supernova, and the first supernova in the universe were unlike anything we see today. When a population 3 star exploded, it released energy equivalent to the entire output of 100 billion suns over its lifetime, compressed into a few weeks. The explosion was so powerful that for a brief moment, this single dying star outshone all the other stars in the early universe, combined. If you could have witnessed it, the flash would have been visible across millions of light years. A beacon, announcing the death of a giant and the birth of complexity. In those violent seconds, something crucial happened. The extreme temperatures and pressures of the supernova allowed fusion to continue beyond iron. Elements that couldn't form in normal stellar cores were created in the chaos: cobalt, nickel, copper, zinc. Through a process called the R process, where atomic nuclei captured neutrons in rapid succession faster than they could decay, even heavier elements began to form: silver, gold, platinum, lead, uranium. And then, traveling at 10,000 to 30,000 kilometers per second, up to 10% of the speed of light, this enriched material blasted outward into space. The star's outer layers, containing all the carbon, oxygen, silicon, and iron forged during its brief life, scattered across light years of distance. For the first time, the pristine hydrogen and helium of the early universe was contaminated, polluted, enriched. These scattered atoms drifted through space, cooling, eventually mixing with vast clouds of primordial gas. When the next generation of stars formed from those clouds, they would be different. They would contain a tiny fraction of heavy elements, perhaps only 0.001% of their mass. But it was enough to change everything. The universe had learned to create complexity, one violent death at a time. The legacy of these first stars extends far beyond their brief existences. They fundamentally transformed the universe's potential, seeding it with the raw materials for everything that would come after. Before population 3 stars, the universe was monotonous. Hydrogen and helium everywhere in nearly identical proportions. No variation, no possibility for the kind of rich chemistry that builds planets and life. But after the first supernovae scattered their enriched ashes, the cosmos became heterogeneous. Some regions contained slightly more heavy elements than others, and that made all the difference. The next generation of stars, population 2 stars, formed from gas clouds that contained these traces of metals, and even a tiny amount of heavy elements changes everything. Carbon and oxygen, even in minute quantities, act as catalysts in cold gas clouds. They help the gas cool more efficiently, allowing clouds to fragment into smaller pieces. This means population 2 stars could form in a wider range of masses, not just as massive giants. Some of these second-generation stars were smaller, longer-lived. They would burn for billions of years instead of millions, providing stable sources of heat and light. They had time to nurture complexity. More importantly, these stars continued the work. In their cores, they fused hydrogen and helium, creating more carbon, oxygen, nitrogen, silicon, iron. When the massive ones died in spectacular supernovae, they scattered even more heavy elements into space. With each stellar generation, the universe's metallicity increased. The abundance of elements heavier than. Helium grew, slowly, steadily, generation after generation. By about 10 billion years ago, the galaxy that would become our Milky Way had been enriched enough that something new became possible. Stars forming from gas clouds contain sufficient heavy elements, perhaps 1% to 2% of their mass, to form rocky planetary systems. Planets with iron cores and silicate mantles. Worlds with solid surfaces. This enrichment was crucial. Without it, Earth couldn't exist. The iron core generating our magnetic field, forged in supernovae, the silicon and oxygen making up the crust, created in stellar cores, the carbon, nitrogen, and phosphorus that would enable life, all manufactured through stellar nucleosynthesis and scattered by stellar deaths. You exist because billions of years ago, massive stars lived briefly and died violently. Those population 3 giants that burned for only a few million years before exploding, they are your ancestors, more directly than any biological lineage. Without their deaths, the atoms in your body could never have been created. The first stars sacrificed themselves so that complexity could emerge, so that, billions of years later, the universe could arrange their scattered atoms into patterns capable of understanding what stars are. Every element in your body heavier than helium passed through at least one stellar core. Some atoms cycled through multiple generations of stars, being incorporated into new stellar furnaces, fused into heavier elements, scattered again, gathered again. Your atoms are veterans of cosmic violence, survivors of explosions that could tear planets apart. And the journey from those primordial supernovae to you required one more crucial ingredient: stars like our Sun. Stars massive enough to forge carbon and oxygen in their cores, but not so massive they'd explode before planets could form. Stars that would burn steadily for billions of years, patient forges creating the exact elements life would need. Take a breath. The oxygen you just inhaled was forged in such a stellar core billions of years ago. Let me show you exactly how. Our Sun is unremarkable. Medium-sized, middle-aged, tucked into an ordinary spiral arm of an ordinary galaxy. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf, though it's actually white when viewed from space. There are billions of stars like it in the Milky Way alone, but this unremarkable star is performing a miracle every single second. At the Sun's core, 150 million kilometers from where you sit tonight, temperatures reach 15 million degrees Celsius. The pressure is 250 billion times Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen nuclei, simple protons, are moving at tremendous speeds, colliding with such violence that they overcome the electromagnetic force that normally keeps positively charged particles apart. When 2 protons collide with enough energy, they can fuse together. But this shouldn't work. 2 protons repel each other. The electromagnetic force pushing them apart is strong, and even at 15 million degrees, classical physics says they shouldn't have enough energy to get close enough to fuse. Enter quantum mechanics, specifically quantum tunneling. In the quantum world, particles don't have precise locations. They exist as probability waves, and there's a small but non-zero chance that a particle can appear on the other side of an energy barrier. It doesn't have enough energy to overcome classically. Protons can tunnel through the electromagnetic repulsion, allowing fusion to occur at temperatures lower than classical physics would predict. Without quantum tunneling, stars couldn't exist. The universe would remain a cold expanse of hydrogen and helium, forever unable to ignite the fusion reactions that power stellar cores. But quantum mechanics makes the impossible merely improbable, and given enough protons colliding trillions upon trillions of times per second, the improbable becomes inevitable. This is the proton-proton chain reaction. 2 protons fuse, forming deuterium, heavy hydrogen with 1 proton and 1 neutron. This process releases a positron and a neutrino. The deuterium nucleus then captures another proton, forming helium-3. Finally, two helium-3 nuclei collide and fuse, creating helium-4 and releasing two protons back into the mix. The net result? 4 hydrogen nuclei combine to create one helium nucleus. But here's the crucial detail. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that formed it. About 0.7% of the mass has vanished. Where did it go? Einstein's equation E=mc2 gives the answer. That missing mass has been converted directly into energy. And because the speed of light squared is an enormous number, 9 followed by 16 zeros, even a tiny amount of mass releases staggering quantities of energy. Every second, the Sun converts 600 million tons of hydrogen into helium. In the process, it loses about 4 million tons of mass, transformed into pure energy. That's the equivalent of 1 million cars' worth of mass simply ceasing to exist as matter and becoming light, heat, and radiation instead. This has been happening every second for 4.6 billion years. The energy released in the core doesn't immediately escape. Photons produced by fusion are absorbed and re-emitted by atoms in the dense plasma. Each photon takes a random walk through the Sun's interior, constantly changing direction as it bounces from atom to atom. A photon produced in the core today will take roughly 100,000 years to random walk its way to the Sun's surface. Only then does it escape into space, traveling the 150 million kilometers to Earth in about 8 minutes. The sunlight warming your skin right now began its journey in the Sun's core 100,000 years ago, when early humans were just beginning to spread across Africa. The energy powering that light came from hydrogen nuclei fusing into helium, converting mass into energy according to the most famous equation in physics. But our Sun, for all its steady brilliance, is too small to create the elements in your body. It will fuse hydrogen into helium for another 5 billion years, but it will never be massive enough or hot enough to forge carbon, oxygen, or iron. For that, we need to look at larger stars, the true element factories of the cosmos. Consider a star 10 times more massive than our Sun. In its youth, it fuses hydrogen into helium in its core, just like the Sun does. But with more mass comes more gravitational pressure, which means higher core temperatures and faster fusion rates. This massive star burns through its hydrogen fuel not in 10 billion years, but in perhaps 20 million years. Eventually, the hydrogen in the core is exhausted. Fusion stops. Without the outward pressure of fusion to balance gravity's inward pull, the helium core begins to contract under its own weight. Here's where things get interesting. As the core contracts, it heats up. Gravitational potential energy converts to thermal energy. The core temperature rises from 15 million degrees to 100 million degrees Celsius. And at that temperature, helium can fuse. 3 helium nuclei, alpha particles in nuclear physics terminology, can combine through a process called the triple alpha process to form carbon. It's a delicate reaction, requiring 3 particles to come together almost simultaneously. But in the dense, hot core of a massive star, it happens constantly. The carbon that forms the backbone of every organic molecule in your body was created this way in the cores of stars that died billions of years ago. But the process doesn't stop there. Once carbon exists in the core, helium nuclei can fuse with carbon to create oxygen. The oxygen you're breathing right now was forged through this reaction in stellar cores when temperatures reached 100 to 200 million degrees. For stars massive enough, those more than about 8 times the Sun's mass, the cycle continues. When the core runs out of helium, it contracts and heats again. At 600 million degrees, carbon begins to fuse, creating neon and magnesium. the core contracts further. At 1 billion degrees, neon fuses into oxygen and magnesium. At 2 billion degrees, oxygen fuses into silicon and sulfur. And finally, at 3 billion degrees, silicon fuses into iron. The star becomes like a cosmic onion with concentric shells of different fusion reactions occurring at different depths. At the center, an iron core grows larger with each passing hour. Around it, a shell of silicon fusing into iron. Beyond that, oxygen fusion. Then neon, carbon, helium, and finally, in the outermost regions, hydrogen fusion continuing in a thin shell around the inert layers below. Each stage of fusion lasts shorter than the one before. The star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, 1,000 years fusing carbon, a year fusing neon, 6 months fusing oxygen, and the silicon fusion stage, the final act before catastrophe, lasts only a few days. During those final days, the star is racing toward its doom, building an iron core that grows by the hour, completely unaware that iron is the end of the line. This layered structure, this onion of fusion shells, is where the elements in your body were created. The carbon in your DNA, triple alpha process in a helium-burning shell. The oxygen in your water, helium fusing with carbon. The magnesium in your chlorophyll if you're a plant, or the magnesium in your enzymes if you're human, carbon fusion. The silicon in the rocks beneath your feet, oxygen fusion. The sulfur in your proteins, oxygen fusion. Each element has a specific birthplace in these stellar layers, forged at specific temperatures and pressures that could only exist in the hearts of dying giants. Your body is a museum of stellar nucleosynthesis, each element an artifact from a different depth in a long-dead star's core. But there's one element that deserves special attention. One element that marks the boundary between creation and destruction. One element that seals the fate of every massive star that dares to forge it. Iron. Iron is special, uniquely, devastatingly special. It sits at the peak of the nuclear binding energy curve, the most stable nucleus in the universe. This means that iron 56, with 26 protons and 30 neutrons, is the most tightly bound arrangement of nucleons possible. For every element lighter than iron, fusion releases energy. Hydrogen to helium, energy released. Helium to carbon, energy released. Carbon to neon, oxygen to silicon, silicon to iron. Energy released every time. This is what powers stars, the energy liberated when light nuclei fuse into heavier ones. But iron breaks the pattern. Fusing iron into heavier elements doesn't release energy. It requires energy. It's endothermic, not exothermic. This is because iron nuclei are already at the optimal configuration. Making them heavier actually makes them less stable, which means you have to put energy in to force the reaction. For a star, this is a death sentence. When a massive star's core fills with iron, nuclear fusion stops. Completely. Suddenly. The furnace that has been burning for millions of years, producing outward pressure that balanced gravity's inward pull, goes cold. There's no more fuel to burn, no more fusion reactions to release energy, no more pressure to resist gravity. And gravity is patient. It has been waiting, compressing the star for its entire lifetime, held at bay only by the heat and pressure of fusion. But now, with fusion stopped, there's nothing to resist it anymore. What happens next occurs in less than a second and ranks among the most violent events in the universe. The iron core, containing perhaps 1.5 times the Sun's mass, compressed into a sphere roughly the size of Earth, begins to collapse. Not slowly, catastrophically. The collapse accelerates. In a quarter of a second, less time than it takes to blink, the core implodes. from Earth-sized to city-sized, from roughly 10,000 kilometers in diameter to about 20 kilometers. The density becomes so extreme that atomic nuclei are crushed together. Electrons, normally held away from the nucleus by electromagnetic repulsion, are forced to combine with protons, forming neutrons. The entire core becomes a single, giant atomic nucleus made of neutrons packed at nuclear density, 1 billion tons per cubic centimeter. A teaspoon of this neutron-degenerate matter would weigh as much as Mount Everest. The collapse happens so fast that it overshoots equilibrium. The core compresses, stops, and rebounds. A shock wave of unimaginable violence races outward through the star's outer layers. This shock wave carries more energy than the star produced in its entire lifetime. As it travels outward, it heats the silicon, oxygen, carbon, and helium layers to billions of degrees, triggering explosive fusion as it passes. The star explodes. This is a core collapse supernova, one of the most energetic events in the universe. For a few weeks, this single dying star will outshine the entire galaxy containing hundreds of billions of stars. The explosion releases more energy in those few weeks than our sun will produce in its entire 10 billion year lifetime. And in that explosion, traveling at 10,000 to 30,000 kilometers per second, up to 10% of the speed of light, the star's outer layers are blasted into space. All the carbon, oxygen, silicon, magnesium, and iron created during the star's life scatter across light years of distance, seeding the interstellar medium with the raw materials for future planets and life. The iron in your blood, the iron that allows hemoglobin to carry oxygen through your body, was created in a stellar core in the final moments before collapse. It was scattered by a supernova explosion so violent it could sterilize planets across dozens of light years. But even supernovae can't create everything. Some elements require conditions even more extreme. There is no warning, no gradual dimming, no final gasping flicker before the end. One moment, a massive star is burning silicon into iron in its core, maintaining the same precarious balance between gravity and fusion pressure it has held for millions of years. The iron core grows larger with each passing hour, accumulating like ash at the bottom of a cosmic fireplace. One solar mass of iron, then 1.2, then 1.4. And then, in less time than it takes to snap your fingers, everything collapses. The collapse begins at the very center of the iron core. A region no larger than a city suddenly gives way. The matter there, held apart by electron degeneracy pressure, the quantum mechanical resistance of electrons being forced into the same space, can no longer resist gravity's crushing weight. The core begins to implode. The collapse accelerates. The inner regions fall first, pulling the outer layers inward behind them. Within 1/10 of a second, the entire iron core, an object with the mass of our sun compressed into a sphere the size of Earth, has collapsed to a ball of neutrons barely 20 kilometers across. From 10,000 kilometers to 20 kilometers in a fraction of a second. The speeds involved are staggering. The innermost layers of the core are falling inward at nearly 1/4 the speed of light, 75,000 kilometers per second. At these velocities, relativistic effects become significant. Time dilation occurs. The collapsing matter experiences time differently than an outside observer would. As the core compresses, electrons and protons are forced together by the extreme pressure. They combine through electron capture, forming neutrons and releasing neutrinos, ghostly particles that barely interact with matter. During the collapse, the star produces more neutrinos in 1 second than our sun will produce in its entire 10 billion year lifetime. These neutrinos carry away enormous amounts of energy, 99% of the supernova's total energy output. They stream outward, through the star, most passing through the outer layers, as if they weren't even there. But the flux is so intense, 1058 particles streaming outward, that even though each individual neutrino has only a tiny chance of interacting with matter, collectively they deposit tremendous energy in the star's outer layers. The collapse continues until the neutrons themselves, packed at nuclear density, can resist no further. Neutron degeneracy pressure, another quantum mechanical effect, finally halts the implosion. The core has become a neutron star, one of the densest objects in the universe, where a sugar cube of matter weighs as much as all of humanity combined. But the collapse has happened so fast, with such momentum, that it overshoots equilibrium. The core compresses slightly beyond its stable radius, then rebounds. Like a compressed spring suddenly released, the core bounces, sending a shockwave racing outward at thousands of kilometers per second. This is the moment of detonation. The shockwave travels through the star's iron core, through the silicon shell, through the layers of oxygen, neon, carbon, helium, and hydrogen. As it passes, it heats matter to billions of degrees. Elements that took millions of years to create are now being manufactured in seconds. The shockwave reaches the star's surface in hours. When it does, the star brightens catastrophically. Within days, the supernova becomes as bright as an entire galaxy of hundreds of billions of stars. From across the cosmos, this single dying star briefly outshines all its neighbors combined. The explosion is so violent that if a supernova occurred within 50 light-years of Earth, the radiation would strip away our ozone layer and cause mass extinction. Fortunately, no massive stars sit that close. But throughout Earth's 3.8 billion-year history, our planet has likely been bathed in radiation from distant supernovae dozens of times. The supernova explosion does something even more important than producing a spectacular light show. It scatters the star's enriched material across space, seeding the interstellar medium with elements that didn't exist when the star was born. The calcium in your bones was created during a supernova explosion, not in the star's core during its lifetime, but in those final violent seconds when the shock wave tore through the outer layers, heating them to billions of degrees. At those temperatures, explosive silicon burning occurred, fusion reactions happening so rapidly that silicon transformed into calcium in mere seconds. The same is true for much of the iron in your blood. While some iron was created in the star's core in those final days before collapse, most iron scattered by supernova was produced during the explosion itself, in hot, dense material just behind the shockwave. Nickel-56 was created first, a radioactive isotope that decays into cobalt-56, which then decays into stable iron-56. This radioactive decay, happening over weeks and months, actually powers the supernova's brightness long after the initial explosion. The iron atom in a hemoglobin molecule in your blood, carrying oxygen from your lungs to your cells, was forged in the extreme conditions of a supernova explosion billions of years ago. It was created in a maelstrom of heat and pressure that would vaporize any planet instantly, scattered into space at 10,000 kilometers per second, and eventually, after billions of years of drifting, incorporated into the molecular cloud that formed our solar system. But the supernova's creative work extends beyond elements like calcium and iron. In the extreme conditions behind the shockwave, where temperatures exceed 10 billion degrees and neutron fluxes are enormous, a process called the R process begins. The R process, rapid neutron capture, occurs when atomic nuclei are bombarded with so many neutrons that they capture them faster than they can undergo radioactive decay. Normally, when a nucleus captures a neutron, It might beta decay over minutes or hours, but in the R process, nuclei capture multiple neutrons in rapid succession, dozens or even hundreds in just seconds before any decay occurs. This builds up extremely neutron-rich nuclei that don't exist under normal conditions. These nuclei then undergo beta decays over the following days and weeks, transforming neutrons into protons and climbing up the periodic table to create elements far heavier than iron. Elements like strontium, zirconium, and barium are primarily created through the R process. So are many rare earth elements crucial for modern electronics. The europium that produces red phosphors in your television or computer screen came from a supernova. The gadolinium used in MRI contrast agents came from explosive nucleosynthesis. The supernova ejects this enriched material at tremendous velocities. The expanding debris field, called a supernova remnant, crashes into the surrounding interstellar medium at thousands of kilometers per second. The collision creates a shock wave that compresses and heats the gas it plows through. This compression can trigger the collapse of nearby molecular clouds, initiating new episodes of star formation. In this way, supernovae are not just deaths, but also births. They destroy stars but create conditions for new stellar generations. They scatter elements necessary for rocky planets and organic chemistry. They enrich the cosmic medium with increasing quantities of heavy elements with each stellar generation. The Crab Nebula, the remnant of a supernova that exploded in 1054 CE, witnessed and recorded by Chinese astronomers, is still expanding today, nearly 1,000 years later. The debris field is now about 11 light-years across and still glowing from the energy of that ancient explosion. At its center sits a neutron star spinning 30 times per second, a lighthouse beacon marking the grave of the massive star that once was. Supernovae are the universe's way of distributing wealth, spreading elements forged in stellar cores across vast distances, ensuring that future generations of stars and planets will be enriched with the building blocks of complexity. For decades, the R process remained one of astrophysics' deepest mysteries. Scientists knew it had to occur. The abundance patterns of heavy elements in the universe could only be explained by rapid neutron capture. But where did it happen? Supernovae seemed like the obvious answer, but calculations showed problems. Typical core collapse supernovae might not produce the extreme neutron-rich conditions necessary for efficient R process nucleosynthesis. The neutron-to-proton ratio in most supernova ejecta appeared too low. The mystery deepened as astronomers studied ancient stars in our galaxy's halo. Stars that formed when the Milky Way was young, containing very low abundances of heavy elements. These stars showed puzzling chemical patterns. Some had large amounts of R process elements, relative to iron, suggesting they had been enriched by events that produced R process elements more efficiently than normal supernovae. What could produce such extreme neutron-rich conditions? The answer came from theoretical predictions made decades earlier, but only confirmed observationally in 2017. Neutron-star mergers. But even before neutron-star mergers were confirmed as major R process sites, researchers realized that certain types of supernovae could contribute. The key is creating neutron-rich outflows from the proto-neutron star left behind by the collapse. When a massive star's core collapses into a neutron star, the newborn neutron star is extraordinarily hot, temperatures exceeding 100 billion degrees. This heat drives powerful winds of neutrons and protons away from the neutron star's surface. These neutrino-driven winds can, under the right conditions, become neutron-rich enough for R process nucleosynthesis. The process works like this. Neutrinos streaming from the hot neutron star interact with the matter in the wind. changing the ratio of neutrons to protons. If conditions are right, if the neutrino luminosity is high enough and the mass loss rate appropriate, the wind becomes neutron-rich. As this material expands and cools, atomic nuclei begin capturing neutrons rapidly, building up heavy elements. Recent research suggests that supernovae from rapidly rotating massive stars, or those producing more energetic explosions called hypernovae, may be particularly efficient R-process sites. The rotation can affect how neutrinos are emitted and how matter flows from the neutron star, creating conditions favorable for heavy element production. What emerges from successful R-process nucleosynthesis is remarkable. In just a few seconds, atomic nuclei transform from iron group elements into elements across the second half of the periodic table. Silver, tin, iodine, xenon, each step adds another neutron to the nucleus, building heavier and heavier isotopes until beta decay begins transforming neutrons into protons. Some of the nuclei produced are stable. Others are radioactive, decaying over hours, days, or years. This radioactive decay releases energy that can power astronomical transients, making supernova remnants glow for months or years after the initial explosion. The iodine in your thyroid gland, essential for producing hormones that regulate metabolism, was likely created through R-process nucleosynthesis. The barium used in medical imaging came from R-process events billions of years ago. Even the tiny amounts of xenon in Earth's atmosphere carry the signature of ancient stellar violence. Every atom heavier than iron in your body carries a history of extreme conditions. They were created in explosions that could obliterate solar systems, forged in temperatures of billions of degrees, scattered at velocities approaching light speed, then slowly, patiently gathered over eons into planets and eventually into you. The universe transforms violence into complexity, chaos into order, destruction into creation. Your existence proves that even the most catastrophic events can, given enough time, become the foundation for something beautiful. But supernovae aren't the only cosmic forges. For the heaviest elements, gold, platinum, uranium, we need to look at collisions even more violent than exploding stars. Take a breath. The story gets even stranger. Imagine two dead stars, each barely 20 kilometers across, each containing more mass than our sun, orbiting each other in the darkness of space. These are neutron stars, the collapsed cores left behind by supernova explosions, objects so dense that a teaspoon of their matter weighs 1 billion tons. They circle each other at tremendous speeds, bound by gravity, locked in an orbital dance that began millions or billions of years ago, when they were both massive stars in a binary system. Both lived their brief, brilliant lives. Both exploded as supernovae, and somehow both remnants remained gravitationally bound, continuing their cosmic waltz even in death. But this dance cannot last forever. As the neutron stars orbit, they emit gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein's general relativity. These waves carry energy away from the system. Slowly, imperceptibly at first, the orbit decays. The neutron stars spiral closer together year by year, century by century. As they draw nearer, the orbital period shortens. They circle each other faster. More gravitational waves are emitted, carrying away more energy, causing the orbit to decay faster still. The process accelerates. What began as a slow spiral becomes a plunge. In the final minutes, the neutron stars are orbiting each other hundreds of times per second, whirling so rapidly that their surfaces move at a significant fraction of the speed of light. The gravitational waves they emit become stronger, their frequency increasing, like a cosmic chirp rising in pitch. And then, after perhaps 10 billion years of slowly spiraling together, the two neutron stars collide. The collision is beyond violent. Two objects, each containing more mass than our Sun, each with surface gravity 200 billion times Earth's, slam together at velocities approaching 100,000 kilometers per second, 1/3 the speed of light. The impact releases more energy in a fraction of a second than our Sun will produce in its entire lifetime. The collision creates a kilonova, an explosion approximately 1,000 times brighter than a classical nova. For days, the kilonova glows with the combined light of hundreds of millions of suns, powered by the radioactive decay of freshly synthesized heavy elements. But the real story isn't the light show. It's what's created in the debris. During the collision and merger, a small amount of neutron-rich material, perhaps 1% to 10% of a solar mass, is ejected into space at tremendous velocities. This material is the most neutron-rich substance in the universe. Pure neutrons, or nearly pure, compressed to nuclear densities and then suddenly released. As this neutron-rich material expands and cools, atomic nuclei begin forming and immediately start capturing neutrons. Not just one or two neutrons, but dozens, hundreds. The R-process nucleosynthesis that struggles to occur efficiently in supernovae happens here with extraordinary productivity. This is where gold comes from, where platinum comes from, where most of the universe's heaviest elements are born, in the violent merger of stellar corpses, in conditions so extreme they existed nowhere else until these two dead stars found each other in the dark and danced their final dance. Every atom of gold on Earth, every atom in every gold ring, every gold filling, every gold bar in every vault, every speck of gold dust in every river, was created in a neutron-star merger billions of years ago. Not in a star's core during its lifetime, not in a supernova explosion. In the collision of two stellar remnants so dense that their matter exists in states that cannot be replicated anywhere else in the universe. Think about what that means. The gold wedding band on someone's finger contains atoms that witnessed the most violent collision imaginable. Those atoms were created when two city-sized objects, each weighing more than our Sun, crashed together at 1/3 the speed of light. They were ejected into space at tens of thousands of kilometers per second, glowing with radioactive heat. They drifted through interstellar space for billions of years, eventually becoming part of the molecular cloud that formed our solar system, condensing into Earth, migrating through geological processes to the surface, and finally being mined and shaped by human hands. The journey from neutron-star collision to jewelry spans billions of years and unimaginable distances, yet here gold sits, inert and beautiful, bearing no outward sign of its violent birth. Platinum is the same. The platinum in catalytic converters, in laboratory equipment, in medical devices, all forged in neutron-star mergers. So is uranium, the heaviest naturally occurring element. The uranium-238 in Earth's core, slowly decaying and producing heat that drives plate tectonics and maintains our magnetic field, was created in a kilonova before our solar system existed. For decades, this was theoretical. Astrophysicists calculated that neutron-star mergers should produce heavy elements efficiently, but there was no direct evidence. The calculations were elegant, the theory compelling, but unproven. Then came August 17th, 2017. On that date, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from two neutron stars spiraling together in a galaxy 130 million light-years away. The signal lasted about 100 seconds, increasing in frequency and amplitude as the neutron stars accelerated toward their final collision. then abruptly cutting off at the moment of merger. But this wasn't just a gravitational wave detection. For the first time, astronomers also observed the electromagnetic counterpart, the light from the explosion. About 2 seconds after the gravitational wave signal ended, gamma-ray telescopes detected a burst of high-energy radiation. Hours later, optical telescopes found a new point of light in galaxy NGC 4993. Over the following days and weeks, astronomers worldwide observed this kilonova at every wavelength. Gamma rays, X-rays, ultraviolet, visible light, infrared, radio waves. They watched it brighten and fade, its color changing from blue to red as the expanding debris cooled. And when they analyzed the spectrum of light, they found exactly what theory predicted: the distinctive signatures of heavy elements being created through rapid neutron capture. The spectral lines of gold, platinum, and other R-process elements were clearly visible. For the first time, humanity had witnessed the cosmic forge where gold is made. We had watched 2 neutron stars collide and seen the birth of heavy elements in real time. The August 2017 detection, officially designated G127081, fundamentally changed our understanding of the universe's chemical evolution. Before this observation, the origin of R-process elements was one of astrophysics' major unsolved mysteries. Now we had proof. When LIGO and Virgo detected the gravitational waves, they immediately sent alerts to astronomical observatories across the globe. Within hours, dozens of telescopes were scanning the sky, searching for the optical counterpart. The SWOPE telescope in Chile found it first, a new point of light in galaxy NGC 4993. Within hours, every major observatory capable of observing that region was pointed at the kilonova. The Hubble Space Telescope, Chandra X-ray Observatory, the Very Large Array, and dozens of ground-based facilities all contributed observations. What they saw matched theoretical predictions with stunning accuracy. The kilonova's early light was blue, coming from the least neutron-rich ejecta heated to tens of thousands of degrees. This material contained lighter R-process elements like strontium and yttrium. As days passed, the emission shifted to redder wavelengths as the ejecta cooled and heavier elements became dominant. The red glow came from lanthanides, elements in the middle of the R process, range, which absorb blue and ultraviolet light efficiently, causing the kilonova to glow red. By modeling the kilonova's light curve and spectrum, astronomers calculated that this single merger produced about 10 Earth masses of heavy elements, including approximately 10 to 20 lunar masses of pure gold. That's between 60 and 120 trillion kilograms of gold, created in seconds and scattered across space. Extrapolating from this event, researchers estimated that neutron star mergers occurring throughout the universe over its 13.8 billion year history have produced enough heavy elements to account for the abundances we observe. The mystery of where gold and platinum come from had been solved through direct observation. The detection also confirmed predictions about gravitational waves. The signal matched Einstein's equations precisely, providing another verification of general relativity under extreme conditions. The waves traveled 130 million light-years, and their properties, amplitude, frequency evolution, waveform shape, all agreed with theoretical calculations. But perhaps most profound was the simple fact that we detected both gravitational waves and light from the same event. Multi-messenger astronomy had arrived. We could now observe the universe through both space-time ripples and electromagnetic radiation, 2 completely different windows onto cosmic phenomena. The gold in jewelry, the platinum in industrial applications, the uranium in Earth's core, all comes from collisions like GW11700. events so rare that they might occur only once every 100,000 years in a galaxy like the Milky Way, but so productive that those rare events have seeded the universe with enough heavy elements to make planets, technology, and life possible. You wear the debris of stellar collisions. The ring on your finger, the filling in your tooth, these are not just precious metals. They are fragments of cosmic violence. Atoms born in collisions so extreme they warp space-time itself, scattered across light years, gathered slowly by gravity into planets, and finally shaped by conscious beings who have no idea they're handling the ashes of dead stars. Take a breath. Every heavy element in your body has a similar story. And now those elements need to find their way from the vastness of space into you. Between the stars, in the vast spaces we think of as empty, there exists a network. An invisible skeleton threading through the galaxy like blood vessels in a living body. Astronomers call it the interstellar medium, the ISM, and it's far from empty. This medium fills the gaps between stars with hydrogen gas, helium, trace elements, and dust grains so fine they're measured in microns. It's incredibly diffuse, far more tenuous than any vacuum we can create on Earth. In the densest regions, you might find a few thousand atoms per cubic centimeter. Compare that to Earth's atmosphere, which contains about 100 billion trillion atoms in the same volume. And yet, despite this extraordinary thinness, the interstellar medium contains roughly 10% to 15% of the galaxy's visible mass. More importantly, it's the reservoir of atoms waiting to become planets, stars, and consciousness. The ISM exists in different states, different temperatures and densities depending on what's nearby. Cold, molecular clouds where temperatures drop to just 10 degrees above absolute zero are the densest regions where gravity can pull gas together to form stars. These clouds can be hundreds of light years across and contain enough material to make millions of stars. Warm regions heated by nearby stars glow faintly in radio and infrared wavelengths. Hot regions blasted by supernova explosions shine in X-rays with temperatures of millions of degrees. The galaxy is not a uniform environment, but a complex, dynamic tapestry of conditions. But there's more to the ISM than just gas and dust. It's threaded with magnetic fields, invisible lines of force stretching across light years, guiding the flow of charged particles and shaping the formation of new stars. These magnetic fields were discovered through observations of starlight. As light passes through dust grains aligned by magnetic fields, it becomes slightly polarized, twisted in a specific direction. By measuring this polarization across the sky, astronomers can map the orientation of magnetic fields throughout the galaxy. What they've found is remarkable. The magnetic fields aren't random. They follow the spiral arms, reinforcing the galaxy's structure. They help regulate star formation by supporting gas clouds against gravitational collapse, at least until those clouds become dense enough that gravity wins. The interstellar medium also contains cosmic rays, high-energy particles accelerated to nearly the speed of light by supernova shock waves and other violent processes. These particles stream through the galaxy, passing through you right now, thousands per second, completely unnoticed. Most are protons, some are heavier nuclei, a few are electrons. Cosmic rays play a crucial role in galactic chemistry. When they collide with molecules in the interstellar medium, they trigger reactions that help form complex organic compounds in molecular clouds. The amino acid precursors, the alcohols, the complex carbon, chains that radio telescopes have detected in space, all owe part of their existence to these energetic particles. The galaxy's magnetic field, threaded through the ISM, acts as a highway for cosmic rays. It helps regulate star formation, can drive galactic winds that carry hot gas away from the disk and channels material from supernova explosions into the halo above and below the galactic plane. This invisible skeleton, gas, dust, magnetic fields, cosmic rays, is what gives the Milky Way its structure. It's the bloodstream of the galaxy, constantly in motion, constantly recycling material, constantly providing the raw ingredients for new generations of stars and planets. And your atoms have been part of this flow for billions of years. The interstellar medium isn't static. It flows, circulates, cycles through different phases in a process that takes millions of years but never stops. When a massive star explodes as a supernova, it doesn't just scatter enriched material into nearby space. The explosion creates a bubble, a cavity hundreds of light years across, carved out by the blast wave and filled with hot, ionized gas. This gas, heated to millions of degrees by the supernova's energy, is too hot to remain in the galactic disk. It rises. Driven by its own thermal pressure and aided by magnetic fields, this hot gas flows upward, away from the galactic plane. It can reach heights of several thousand light-years above the disk, forming what astronomers call the galactic halo, a diffuse, hot atmosphere surrounding the flat spiral. But what goes up must come down. As the hot gas rises, it expands and cools. Eventually, it reaches a point where it's no longer buoyant enough to rise further. Gravity takes over. The gas begins to fall back toward the disk, condensing as it cools, eventually forming cold clouds that rain back down onto the galactic plane. This is the galactic fountain, a circulation pattern where hot gas from supernovae rises into the halo, cools and falls back as cold clouds that can form new stars. The cycle takes roughly 100 million years to complete. Material is constantly being lifted from the disk, circulated through the halo, and returned to the disk in a slow, stately flow. This circulation is crucial for distributing heavy elements throughout the galaxy. Without it, elements forged in stars near the galactic center would stay there, concentrated in the inner regions, unable to reach the outer parts of the disk, where our sun eventually formed. The presence of heavy elements in the sun and Earth is evidence that this circulation has been operating for billions of years, mixing material from across the galaxy. Every supernova near the galactic center over the past 10 billion years has contributed atoms that eventually traveled outward through the galactic fountain, enriching the gas clouds in the outer disk. Your iron atoms might have been forged in a supernova near the galactic core 8 billion years ago. Lifted into the halo by the explosion's energy, cooled over millions of years, while drifting thousands of light-years above the disk, then fallen back into the spiral arms where our sun formed 4.6 billion years ago. The fountain also helps regulate star formation. By removing hot gas from the disk and returning it as cold clouds, the fountain prevents all the galaxy's gas from being converted into stars too quickly. Without this circulation, the Milky Way would have exhausted its gas supply billions of years ago, and no new stars would form today. The galactic fountain is powered by stellar deaths. Every supernova contributes energy to drive the circulation. Every massive star that explodes pumps more hot gas into the halo, maintaining the flow. It's a self-sustaining system where stellar evolution drives galactic-scale circulation that enables future stellar evolution. You are made of atoms that have ridden this fountain. They've been lifted by explosions, cooled in the halo, fallen back to the disk, been incorporated into new stars, perhaps even cycled through the fountain multiple times before finally settling into the molecular cloud that formed our solar system. The galaxy breathes, and you are made of its breath. The The coldest, densest regions of the interstellar medium are where the galaxy's future is written. These are the molecular clouds, vast dark structures where temperatures drop to just 10 or 20 degrees above absolute zero, and densities reach levels high enough for gravity to begin its work of star formation. The most famous molecular cloud visible from Earth is the Orion Nebula, a stellar nursery about 1,300 light-years away. On a clear winter night, you can see it with the naked eye as a fuzzy patch in Orion's sword. Through a telescope, it's spectacular. A glowing region of gas and dust lit by the ultraviolet radiation from hot, young stars being born within it. But what makes molecular clouds truly remarkable isn't just that stars form there. It's the complex chemistry occurring in their dark, cold interiors. Radio telescopes have detected over 200 different types of molecules floating in interstellar space. Not just simple molecules like molecular hydrogen, H2, or carbon monoxide, CO, but complex organic compounds: water, ammonia, methanol. Ethanol? Yes, alcohol exists in space, in vast clouds containing more than all the alcohol humans have ever produced. Formaldehyde, acetic acid, even amino acids, the building blocks of proteins, have been detected in meteorites that originated from these clouds. This chemistry happens despite the extreme cold and low density. Cosmic rays and ultraviolet light from distant stars provide energy to drive chemical reactions. Dust grains act as catalysts, providing surfaces where atoms can meet and bond. Slowly, over millions of years, simple atoms combine into increasingly complex molecules. When our Sun formed 4.6 billion years ago, it condensed from a molecular cloud that already contained these organic compounds. The cloud wasn't just hydrogen and helium, it was pre-enriched with water, ammonia, and organic molecules synthesized in the interstellar medium over hundreds of millions of years. These molecules were incorporated into the protoplanetary disk, the swirling disk of gas and dust around the young sun from which planets would form. Some became part of comets and asteroids. Some were incorporated directly into the planets. Earth inherited its water and organic compounds from this primordial inventory. The first oceans that formed on Earth's surface 4 billion years ago contained water molecules that had existed in interstellar space. The organic compounds that eventually led to the emergence of life. The amino acids, the sugars, the lipids, built upon chemistry that began in the cold darkness between the stars. Life didn't start from scratch. It started with a library of complex molecules already written by cosmic chemistry. The interstellar medium provided the vocabulary. Earth provided the environment where that vocabulary could be arranged into sentences, paragraphs, chapters. The story of biology. You are the descendant of interstellar chemistry. The molecules in your body trace their lineage back through Earth's geological history, through the formation of the solar system, through the molecular cloud that gave birth to the sun, back to the cold, dark nurseries where cosmic chemistry first wrote the precursors of life. Take a breath. The oxygen molecule you just inhaled has a history spanning the galaxy. And now, finally, we can trace how those atoms found their way specifically into you. Our sun is a latecomer to the cosmic story. When it ignited 4.6 billion years ago, the universe was already 9.2 billion years old, 2/3 of its current age. The first stars had lived and died billions of years before our sun was born. Entire generations of stellar evolution had already run their course. This timing matters profoundly. Our sun didn't form from the pristine hydrogen and helium of the early universe. It formed from gas that had been processed, enriched, and transformed by countless previous stars. Astronomers call our sun a population 1 star, part of the youngest, most metal-rich generation of stars currently forming in galaxies. The distinction is crucial. Population 3 stars were the first, massive, short-lived giants made of pure primordial gas. They forged the first heavy elements and scattered them through space when they exploded. Population 2 stars formed from slightly enriched gas, containing traces of heavy elements from population 3 supernovae. They continued the work, creating more carbon, oxygen, and iron. And then came population 1 stars like our Sun, born from gas clouds already enriched by billions of years of stellar processing. The molecular cloud that collapsed to form our solar system contained approximately 2% heavy elements by mass. That might sound small, but it represents billions of years of stellar alchemy. Every atom heavier than helium in that cloud had cycled through at least one previous star, possibly several. Think about what that means. The atoms in the Sun weren't created 4.6 billion years ago. They're far older. The hydrogen dates back 13.8 billion years to the Big Bang. The carbon, oxygen, and iron were forged in stars that lived and died between 5 and 10 billion years ago, scattered by supernovae long before our solar system existed. When the molecular cloud that would become our solar system began to collapse under its own gravity, it was already a mixture of elements from dozens, possibly hundreds of different stellar sources. Some iron atoms came from one supernova, some from another. Carbon atoms originated in various red giant stars. Gold atoms came from different neutron star mergers scattered across billions of years. The cloud wasn't uniform either. Different regions had slightly different compositions, different ratios of elements, depending on which stellar deaths had contributed material nearby. This chemical heterogeneity is still visible in meteorites today, ancient rocks that preserved the original composition of the protoplanetary disk show subtle variations in isotope ratios, signatures of different stellar sources. Our Sun is a composite, a mosaic built from the ashes of many predecessors. It carries within it the legacy of stellar evolution, stretching back nearly to the universe's beginning. Every heavy element in the Sun's atmosphere was created elsewhere, in other stars, other explosions, scattered across space and slowly, patiently gathered by gravity into the cloud that would become our solar system. We are third-generation star material at minimum, possibly fourth or fifth generation for some atoms that cycled through multiple stellar lifetimes before ending up in the Sun. This multi-generational heritage is written in the Sun's spectrum, the fingerprint of elements revealed when sunlight is split into its component wavelengths. The Sun is unremarkable by cosmic standards, a middle-aged, medium-sized yellow dwarf in a quiet corner of the galaxy. But its chemical composition, its metallicity, made all the difference. Because without that 2% of heavy elements, Earth couldn't exist. Metallicity, the abundance of elements heavier than helium, turns out to be one of the most important factors determining whether a star can host habitable planets. Too little, and you can't build rocky worlds. Too much, and you might create something entirely different. Stars with very low metallicity, those from the galaxy's early generations, form from gas, clouds containing almost no heavy elements. When such a star forms, the protoplanetary disk surrounding it is nearly pure hydrogen and helium. These elements remain gaseous even at extremely low temperatures. They can't condense into solid particles. They can't accrete into rocky planets. Low metallicity stars might form gas giants, massive planets like Jupiter composed primarily of hydrogen and helium. But they're unlikely to form Earth-like rocky planets with solid surfaces, liquid water oceans, and the chemical complexity necessary for life as we know it. On the other extreme, stars with very high metallicity form from gas clouds exceptionally rich in heavy elements. Their protoplanetary disks contain abundant solid material, silicates, iron, carbon compounds. Planets form readily. But here's the problem. With so much solid material available, planets might grow too large too quickly. Instead of stopping at Earth size, they continue accreting material, building up thick atmospheres of hydrogen and helium captured from the surrounding disk. The result is mini Neptunes, planets several times Earth's mass with massive gas envelopes. These worlds might have rocky cores, but their surfaces are buried beneath thousands of kilometers of thick, crushing atmosphere. Our Sun sits in the sweet spot. Its metallicity of approximately 2% was just right, enough heavy elements to build substantial rocky planets like Earth, Mars, Venus, and Mercury, but not so much that those planets became bloated mini-Neptunes. The balance allowed Earth to form with the right mass, the right composition, the right distance from the Sun. This sweet spot is why astronomers searching for potentially habitable exoplanets pay close attention to stellar metallicity. Stars with solar-like metallicity between about 0.5% and 3% heavy elements are prime candidates for hosting Earth-like worlds. Too far outside this range, and the chances of finding habitable planets drop significantly. But metallicity affects more than just whether rocky planets can form. It also influences the types of chemistry available on those planets. Earth's iron core, which generates our protective magnetic field, required substantial iron in the protoplanetary disk. That iron came from previous supernovae. Without it, Earth might not have developed the magnetic field that shields our atmosphere from being stripped away by the solar wind. The silicon and oxygen that make up Earth's mantle and crust, 90% of the planet by volume, came from stellar nucleosynthesis in previous generations of stars. The carbon that would eventually enable organic chemistry came from red giants. The phosphorus essential for DNA and cellular energy storage came from supernova nucleosynthesis. Every element necessary for Earth's geology and biology was present in the molecular cloud, because previous stars had created and scattered them. The Sun's metallicity represents the accumulated chemical enrichment of billions of years of stellar evolution in our region of the galaxy. And the timing was crucial. The Sun formed when the galaxy was old enough to have enriched the interstellar medium with sufficient heavy elements, but young enough that plenty of gas remained for star formation. Earlier, and the metallicity would have been too low. Much later, and the galaxy might have exhausted its gas supply. We exist in a special moment in galactic history, after enough stellar processing to create the elements we need, but before the galaxy exhausted its resources. The Sun formed at just the right time, from gas, with just the right composition, in just the right location. 4.5 billion years ago, a giant molecular cloud in the Milky Way's Orion arm began to collapse. Perhaps triggered by a nearby supernova's shockwave, perhaps by gravitational instabilities within the cloud itself, the collapse accelerated. As gas fell inward, the cloud spun faster, conservation of angular momentum. At the center, a protostar formed, what would become our Sun. But not all material fell directly into the growing star. Much of it settled into a rotating disk, the protoplanetary disk from which planets would eventually form. This disk was hot near the Sun and cold farther out. Close to the protostar, temperatures exceeded 1,500 Kelvin, hot enough to vaporize rock. Only the most refractory materials, metals like iron and nickel, could exist as solids. Farther out, beyond the frost line at about 3-4 astronomical units from the Sun, temperatures dropped below water's freezing point. Ice could form. Volatile compounds could condense. This temperature gradient created different planetary building blocks at different distances. Near the Sun, tiny grains of metal and rock collided and stuck together. These dust particles grew from microscopic grains to pebbles, to boulders, to kilometer-sized planetesimals through accretion. Planetesimals then underwent further collisions, some gently merging, others violently smashing together. The larger planetesimals had stronger gravity, attracting more material, growing faster. This runaway growth created planetary embryos, Moon to Mars, sized objects scattered throughout the inner solar system. Earth formed through the collision and merger of these planetary embryos. It wasn't gentle. Impacts between embryos released tremendous energy, melting the growing planet. Early Earth was a molten ball of rock, its surface a magma ocean hundreds of kilometers deep, glowing red-hot from impact energy and radioactive decay. In this molten state, gravity sorted materials by density. The heaviest elements, primarily iron and nickel, sank toward the center, forming Earth's iron core. This differentiation was crucial. The iron core, making up about 1/3 of Earth's mass, would eventually generate the magnetic field, protecting life from solar radiation. Lighter elements, silicon, oxygen, magnesium, aluminum, rose to form the mantle, and eventually, the crust. The iron sinking to Earth's center came from supernovae. The silicon and oxygen forming the mantle came from stellar nucleosynthesis. Every layer of Earth's structure is built from atoms with distinct stellar origins. The final major impact, the collision with a Mars-sized body called Theia about 4.5 billion years ago, ejected enormous amounts of material into orbit. This debris coalesced to form the Moon. The impact theory explains why the Moon has a similar composition to Earth's mantle, but lacks a substantial iron core. It was formed from Earth's outer layers, material that had already differentiated. After the Moon-forming impact, Earth slowly cooled. The magma ocean solidified. A crust formed. And eventually, once temperatures dropped enough, water vapor in the atmosphere condensed, raining down to form the first oceans about 4.4 billion years ago. Those oceans contained water molecules from the primordial molecular cloud, water that had existed in interstellar space long before the Sun formed. And dissolved in that water were trace amounts of organic compounds, also from the molecular cloud, that would eventually organize themselves into the first living cells. Earth had become a stage where stellar atoms could arrange themselves into biology. For the first few 100 million years of Earth's existence, the planet was lifeless. The surface was molten, then gradually cooling. Heavy bombardment from asteroids and comets continued, each impact delivering water and organic compounds, but also sterilizing the surface with heat and radiation. The environment was hostile. No oxygen in the atmosphere, intense ultraviolet radiation from the Sun, volcanic activity reshaping the landscape constantly. But somewhere, somehow, around 3.8 to 4 billion years ago, chemistry became biology. We don't know exactly how it happened. The origin of life remains one of science's great mysteries, but we know the ingredients were present. Organic molecules from the interstellar medium delivered by comets and synthesized in Earth's atmosphere through lightning and UV radiation. Water, providing a medium for chemical reactions. Energy sources, sunlight, lightning, volcanic heat, chemical gradients in hydrothermal vents. In some location, perhaps in warm, shallow pools, perhaps in deep ocean hydrothermal vents, perhaps in mineral-rich clay deposits, molecules began to self-replicate. RNA or something like it emerged, capable of storing information and catalyzing reactions. Lipid membranes formed, creating boundaries between inside and outside, defining the first protocells. These early organisms were simple beyond imagining, single-celled, lacking nuclei, probably similar to modern bacteria. But they possessed the fundamental characteristic of life. They could reproduce, passing information to offspring, subject to mutation and natural selection. And they were made entirely of stellar atoms. The carbon forming the backbone of their RNA came from red giant stars. The phosphorus in their genetic material came from supernovae. The oxygen in their water came from massive stars that fused helium and carbon. The iron in their primitive enzymes came from stellar cores that collapsed into neutron stars. The nitrogen in their proteins came from carbon-nitrogen-oxygen cycle fusion in intermediate mass stars. Every atom in the first living cell had traveled billions of years to reach that moment. Each had been through stellar cores, supernova explosions, interstellar clouds, the formation of the solar system, Earth's differentiation and cooling, geological cycles bringing material to the surface. And now, for the first time, these atoms were arranged into patterns that could maintain themselves, reproduce, and evolve. Life began to transform Earth. Photosynthetic organisms emerged, using sunlight to split water molecules and release oxygen as waste. This was revolutionary. Free oxygen was toxic to most early life forms, but it also opened new possibilities. Oxygen-breathing organisms could extract far more energy from food than anaerobic ones. Complex multicellular life became possible. The oxygen you breathe, the oxygen that makes up 21% of Earth's atmosphere, was created by living things. Not all at once, but gradually, over billions of years. Cyanobacteria and later plants split water molecules using energy from the sun. Energy produced by fusion in the solar core, itself descended from hydrogen, created in the Big Bang. Every breath you take connects you to this history. The oxygen molecule entering your lungs right now was created by stellar nucleosynthesis billions of years ago, scattered by a supernova, incorporated into Earth, cycled through geology, released by a plant through photosynthesis, and now entering your bloodstream to power your cells. You are not just made of stellar atoms. You are made of stellar atoms that have been transformed by 4 billion years of biological evolution on Earth. Every thought you think, every movement you make, every heartbeat, every breath, all of it is powered ultimately by the sun, not just metaphorically, literally. Plants capture sunlight using chlorophyll, a molecule built around a magnesium atom, created by carbon fusion in a massive star, surrounded by a ring of carbon and nitrogen atoms. When photons from the sun strike chlorophyll, their energy excites electrons, triggering a cascade of chemical reactions that convert carbon dioxide and water into glucose and oxygen. This glucose stores energy in the bonds between carbon atoms, energy that originated 93 million miles away in the sun's core, where hydrogen nuclei fused into helium, converting mass into energy. That energy spent 100,000 years random walking through the sun's interior, emerged as light, crossed space in 8 minutes, struck a plant leaf, and became locked in chemical bonds. When you eat, you're consuming this stored sunlight. Your digestive system breaks down food molecules, carbohydrates, fats, proteins, releasing the energy in their chemical bonds. This energy is transferred to ATP, adenosine triphosphate, the universal energy currency of life. ATP is a remarkable molecule. It contains adenine, made of carbon and nitrogen atoms, ribose, AITA, sugar built from carbon, hydrogen, and oxygen, and 3 phosphate groups containing phosphorus atoms created in supernova nucleosynthesis. The bonds between phosphate groups store energy. Breaking these bonds releases energy that powers everything your cells do. Every muscle contraction uses ATP. Every nerve impulse uses ATP. Every protein your cells synthesize requires ATP. Every time your heart beats, millions of ATP molecules are broken down to release energy, then reassembled to store energy again. Your body cycles through its entire body weight in ATP every day, about 60 kilograms of ATP synthesized and broken down continuously. And the energy for all of this ultimately traces back to fusion reactions in the sun's core. You are powered by starlight, not poetically, physically. The energy gradient between glucose and carbon dioxide plus water, the energy your mitochondria extract through cellular respiration, originated as mass converted to energy in the sun's core through ERMC2. But there's another layer to this. The sun itself is powered by hydrogen created in the Big Bang. The fusion reactions converting hydrogen to helium are releasing energy stored in those hydrogen nuclei 13.8 billion years ago, when the universe was 15 minutes old. In a sense, you're powered by the Big Bang itself, by energy locked into matter at the universe's beginning, released through stellar fusion, captured by photosynthesis, stored in chemical bonds, and finally liberated in your mitochondria to power your metabolism. Every calorie you burn connects you to the cosmos's deepest history. The energy in the glucose molecule powering your brain as you process these words originated in the first minutes of creation, was locked into hydrogen nuclei, stored for billions of years until that hydrogen fell into a molecular cloud that became the sun. Fused in the solar core, emerged as light, was captured by a plant, stored in chemical bonds, consumed by you, and is now powering the neurons firing in your brain. You are not just made of stars, you are powered by stars. Your consciousness runs on ancient starlight filtered through 4 billion years of biological evolution. Here's where the story becomes strange and beautiful in equal measure. The same laws of physics that govern stellar fusion also govern your consciousness. The quantum mechanics that allows protons to tunnel through electromagnetic barriers in the sun's core also governs the electron transport chain in your mitochondria. The same physics that explains how stars shine explains how your cells extract energy from food. The electromagnetic force that holds atoms together in stellar cores is the same force holding the molecules of your body together. The weak nuclear force that allows hydrogen to fuse into helium in stars is the same force involved in radioactive decay in your body. The radioactive potassium-40 and carbon-14 that exist in trace amounts in your tissues. Gravity, which collapses molecular clouds to form stars, also keeps your feet on the ground, keeps Earth in orbit around the sun, keeps your blood flowing downward when you stand up. The same fundamental force operating across light years operates in your body constantly. The laws of thermodynamics that dictate how stars evolve also dictate how your metabolism works. Stars fight against entropy, maintaining order through fusion that converts mass to energy. You fight against entropy, maintaining order through metabolism that extracts energy from food. Both processes are temporary. Stars eventually run out of fuel. You eventually die. Entropy always wins in the end. But for a time, billions of years for stars, decades for humans, localized order can be maintained. Even consciousness itself, mysterious as it is, must ultimately be a physical process governed by the same laws that govern everything else in the universe. The neurons in your brain are made of atoms obeying electromagnetic forces. The electrical signals propagating along nerve fibers follow the same principles as electrical currents anywhere. The chemical synapses releasing neurotransmitters operate through molecular interactions governed by quantum mechanics. We don't fully understand consciousness. How subjective experience emerges from physical processes remains one of science's deepest mysteries. But whatever consciousness is, it must be compatible with physics. It can't violate conservation of energy or quantum mechanics or relativity. It emerges from matter, from atoms forged in stellar cores, arranged in patterns complex enough to generate thoughts, feelings, awareness. In a sense, consciousness is the universe understanding itself. Stellar atoms, processed through billions of years of cosmic evolution, arranged into brains capable of asking questions about stellar atoms. The cosmos folded back on itself, creating structures complex enough to contemplate their own origins. When you look up at the night sky and feel awe, you're experiencing stellar matter arranged into neurons responding to photons from distant stellar matter. When you read about nucleosynthesis and understand it, you're using atoms created by nucleosynthesis to comprehend nucleosynthesis. The universe is using you, using your brain, your consciousness, as a tool to understand itself. You are not separate from the physical universe. You are the physical universe, temporarily organized into a pattern capable of wonder, curiosity, and understanding. The atoms in your brain were forged in stellar cores. The energy powering your thoughts comes from the sun. The laws governing your neurons are the same laws governing galaxies. You are physics made conscious. Starlight aware of itself. The cosmos awakened. Let's trace one atom's journey from beginning to end. One carbon atom currently residing in your left hand. 13.8 billion years ago, it didn't exist. The universe was pure hydrogen and helium, too simple to create it. For hundreds of millions of years, this remained true. The cosmos drifted in darkness, waiting. Then, perhaps 200 million years after the Big Bang, a massive population 3 star collapsed from a primordial gas cloud. In its core, temperatures reached 100 million degrees. 3 helium nuclei collided almost simultaneously, the triple alpha process, and your carbon atom was born. For a few million years it existed in the stellar core, surrounded by the violence of ongoing fusion. When the star exhausted its fuel, the core collapsed. The star exploded as a supernova. Your carbon atom was scattered into space at 15,000 kilometers per second, part of an expanding debris field that would eventually stretch across hundreds of light years. It drifted for perhaps 1 billion years. It floated through the interstellar medium, occasionally joining with other atoms to form carbon monoxide molecules, then being broken apart by ultraviolet radiation, then joining again. It was part of the galaxy's slow circulation, caught in currents of gas moving through the spiral arms. Eventually, it became part of a second-generation star. This star lived, fused its hydrogen and helium, created more heavy elements, and it too died, scattering your carbon atom once more. Perhaps this happened twice, 3 times, each cycle adding to the enrichment of the galaxy. About 9 billion years after its creation, your carbon atom was floating in the Orion arm of the Milky Way when a nearby supernova triggered the collapse of a giant molecular cloud. The carbon atom, along with trillions of others, fell inward as the cloud contracted. It became part of the protoplanetary disk around the young sun. Through countless collisions over millions of years, it accreted into a planetesimal, then a planetary embryo, then became part of Earth itself. It was buried in the mantle, cycled through plate tectonics, eventually brought to the surface through volcanic activity. It became part of the atmosphere as carbon dioxide. A cyanobacterium absorbed it 2 billion years ago, incorporating it into organic molecules. For eons, it cycled through the biosphere, part of bacteria, algae, plants, animals. It was exhaled and inhaled countless times. It was part of a trilobite in ancient seas, a fern in carboniferous forests, a dinosaur in the Mesozoic, a small mammal in the Cenozoic. Recently, perhaps a few months ago, it was part of a plant. You ate that plant or ate an animal that ate that plant. The carbon atom was absorbed through your digestive system, entered your bloodstream, and was incorporated into a protein molecule in your left hand. There it sits now, in your hand. After 13.8 billion years, after stellar cores and supernova explosions, after drifting through interstellar space and cycling through the biosphere, this carbon atom is temporarily part of you. You are not an alien intruder in an indifferent cosmos. You are the cosmos itself, arranged into a pattern capable of understanding what you are. Every atom in your body has a biography spanning the history of the universe. You are the product of billions of years of cosmic evolution, stellar nucleosynthesis, galactic recycling, and biological adaptation. You are exactly where you belong. You are home. Tonight, as you settle into stillness, as your breathing slows and consciousness begins to drift, remember what you are. You are 7 octillion atoms, each one a time traveler, each one carrying stories of violence and creation, of explosions and patient accumulation, of heat beyond imagining and cold beyond measure. The calcium in your bones was forged in a supernova that outshone a galaxy. The iron in your blood was created in the final second before a stellar core collapsed. The oxygen you're breathing was made in a massive star that died before the sun was born. You are not separate. You have never been separate. The distinction between you and the universe is arbitrary, a convenient fiction for navigating daily life, but not ultimately true. The atoms in your hand right now will be in the soil tomorrow, in a plant next year, in another person in a decade. You are a temporary arrangement, a brief pattern in the endless flow of matter through the cosmos. But what a pattern! What a spectacular arrangement! Complex enough to read these words, complex enough to understand your own origin, complex enough to feel awe at the realization that you are made of stars. The universe is 13.8 billion years old. Stars have been forging elements for most of that time. You are the beneficiary of nearly 14 billion years of cosmic alchemy, the recipient of countless stellar deaths, the inheritor of generations of galactic enrichment. And you are temporary. The atoms that currently compose you will return to the world. They'll be recycled, as they have been recycled for billions of years. They'll become part of other patterns, other structures, other moments of consciousness. The carbon in your cells will be exhaled as carbon dioxide, absorbed by plants, eaten by animals, returned to soil, cycled endlessly through the biosphere. In a sense, you are the universe's way of experiencing itself. For a few decades, these stellar atoms are arranged in a configuration that can think, feel, wonder, and understand. And then that configuration dissolves, and the atoms move on to other adventures, other forms, other expressions of cosmic creativity. But right now, in this moment, they are you. And in being you, they are participating in something remarkable: consciousness, awareness, the capacity to understand where they came from and what they are. The spiral holds you. It has always held you. Since before you were born, since before Earth formed, since before the sun ignited. The galaxy has been preparing for this moment. Every supernova, every stellar birth, every collision and merger, and patient accumulation, it all led here, to you, tonight. If this journey through your own ancient history brought you a moment of wonder, if something shifted in how you see yourself and the cosmos you're part of, a gentle like or subscribe to Space Doze would mean everything. It's a small gesture, just a click, but it tells me you're out there, breathing with the stars, drifting through cosmic mysteries, remembering what you've always been. It keeps this space alive, this quiet corner of the internet where we explore the universe together, where science becomes poetry and facts become doorways to wonder. Leave a comment if you'd like. Tell me which part of this journey resonated most. Was it learning that hydrogen in your body is 13.8 billion years old? That gold comes from neutron star collisions? That you're powered by ancient starlight? I read every comment, and they often inspire future explorations into the cosmic mysteries we're still unraveling. And if you know someone who might appreciate this, someone who looks up at the stars and feels that pull, that sense of connection, that curiosity about where we come from, share this with them. These stories are meant to be passed along like the atoms themselves, moving from person to person, sparking wonder wherever they go. Thank you for drifting through these mysteries with me tonight. Thank you for being here, for listening, for caring about the deep time story written in your own atoms. You make this possible. The universe spent 13.8 billion years arranging atoms in increasingly complex patterns. And tonight, one of those patterns, you, spent time understanding how it came to be. That's beautiful. That matters. Now rest. Let the stars turn above you. Let the galaxy carry you gently into sleep. Sleep well, Stardust. You are not just in the universe. You are not just of the universe. You are the universe. Briefly awake, briefly aware, briefly capable of looking back at the vast cosmic machinery that created you and saying, I understand. The hydrogen in your water was manufactured in the Big Bang's first 15 minutes. The carbon in your cells was forged in red giant stars. The iron in your blood was scattered by supernovae. The gold in any ring you wear came from colliding neutron stars. Every element heavier than helium required stars to create it, required stellar deaths to scatter it, required billions of years to gather it into you. You are a mosaic of stellar deaths, a walking, breathing, thinking collection of ancient atoms that have witnessed the birth of galaxies, survived supernova explosions, drifted through light years of space, and finally, after an unimaginable journey, arranged themselves into the temporary pattern called you. The atoms will move on. But for now, they are home in you. Close your eyes. Feel your breath. Know that you are exactly what the universe has been building toward for 13.8 billion years. You are the cosmos, experiencing itself. Sleep well, Stardust. You are home. Good night.